The past two lectures have focused on the seemingly different phenomenon of magnetism and electricity. You know that magnetic poles attract each other, opposites attract, like poles repel. And also electric charges can attract or repel each other. Indeed, you can use electrical forces to push electrons through a wire and create electricity. In this lecture, I'm going to combine these two concepts in one of the transforming principles of science, that electricity and magnetism are two aspects of the same force. The connection between magnetism and electricity came in two steps, and these frame the first two-thirds of this lecture. First is the discovery that electricity can produce magnetic fields, the principle of the electromagnet. Then it follows the symmetrical idea that moving magnets can produce electricity. That's the principle of the electric generator. In the last third of Lecture 13, I'm going to introduce the great Scottish physicist James Clerk Maxwell, who synthesized electricity and magnetism into one elegant mathematical formalism. To begin, let's review briefly what we've learned about electricity and magnetism. These two phenomena are seemingly quite different. Magnetic forces seem to be an attribute of a few odd materials, iron, the mineral magnetite, several other solids, but not very many. And these incorporate a north and a south magnetic pole, something that's intrinsic to those materials. All magnets have these two poles. Magnets are always physical objects. They have seemingly permanent properties. Electrical forces, on the other hand, appear all around us. Whenever an object accumulates a surplus or a deficiency of electrons, a positive or a negative charge, if you will. Electrically charged objects will typically be either positive or negative, depending on that surplus or deficiency of electrons. These electric charges seem quite transient. You can charge up an object, the object can lose its charge, and we see these phenomena all around us. But of course, there are also some very important similarities between these two forces. These forces set electricity and magnetism apart from, for example, gravity. In each case, the force can be either attractive or repulsive. That's very different from gravity, which is always only attractive. In each case, like poles or like charges repel each other, whereas opposite poles or opposite charges attract each other. Well, in any event, whatever the nature of electricity and magnetism, Newton's clear definition of a force allows this is a phenomenon that allows a mass to accelerate. It allows both electricity and magnetism to be studied by scientists who wanted to understand the nature of the everyday phenomenon in our world. So electricity and magnetism, of course, were intensely studied 17th, 18th, and into the 19th century. The beginning of electricity's modern era can be traced to a small Danish college classroom in 1820. There, in front of a room full of physics students, it was Professor Hans Christian Ørsted who discovered that electricity can produce magnetic fields. And this was a transforming event in the science of electromagnetism. Let me tell you a little bit about Ørsted. He was born in 1777. He was the elder son of a Danish pharmacist, and from an early age he had planned to follow his father's profession of pharmacy. But he became captivated by electrical studies in 1800, shortly after Volta's announcement of the battery. You can imagine how the invention of this battery, where you had a continuous flow of electrical current, really changed a lot of people's lives, because suddenly you could study this new phenomenon in a laboratory environment in a totally new way and learn all sorts of things that no one had ever known before. The young Hans Ørsted excelled as a student in languages, in mathematics, and in science. He was homeschooled, but he passed the entrance examinations and enrolled in the University of Copenhagen in 1794 at the young age of 17. He received degrees in both pharmacology and in Kantian philosophy, of all things, and he was for a short time thereafter a manager of a pharmacy. But eventually he turned his attentions full-time to science. That was his real love. While still in his 20s, Ørsted secured visits to many of the famous laboratories in Europe, and he was able to learn the types of research that were going on in these other laboratories. He also was able to gain entrance to these laboratories and gain respect because he himself invented an improved compact battery, a battery that was quite powerful but very small and portable. He returned to Denmark in 1804, and he had hoped very much to secure a faculty appointment at the University of Copenhagen. But such a post was not immediately forthcoming, much to his disappointment. He therefore turned to public lecturing, and he did scientific demonstrations for the public on electrical phenomena. He was so successful and so popular that he was given a professorship almost by demand at the University of Copenhagen in 1806 because he was so good at bringing science to the public. Ørsted liked to read and tried to interpret Kantian philosophy, and this led him to believe that the various forces in nature, including magnetism and electricity, must somehow stem from the same, what he called, original power. He saw a unity in the universe, and the forces all had to be one and the same, he felt. He was therefore predisposed to observe links between electricity and magnetism that other people might not have seen. So it was in the winter of 1820 that Ørsted made his most famous discovery. This is what he did. He was performing demonstrations in electricity and magnetism in front of this classroom. He hooked up a coil of wire to a battery and passed a current through that coil of wire. And he observed that a compass needle next to the coil twitched whenever he did this. I can reproduce that quite easily. I have a coil of wire wrapped around a nail and a battery. When you close the circuit near a compass needle, you see how that compass needle twitches? Clearly, the coil of wire is producing a magnetic effect. And Ørsted, in 1820, in front of a Danish classroom, was the first to discover this phenomenon. After several weeks of experimentation, he announced that electricity passing through a curved path produces a magnetic field. By July of 1820, he had submitted a manuscript describing this link between electricity and magnetism, and this, in fact, was the great discovery of the fact that electricity produces magnetic fields. Prior to Ørsted, electricity and magnetism were viewed as two completely separate phenomena. They involved very different kinds of physical situations and conditions, but here Ørsted unified this work by showing that one phenomenon was intimately linked to the other. With the battery, of course, you can convert electrical potential energy into chemical potential energy. That's the decomposition of water and heat and light. Ørsted showed that you could also convert that into magnetic potential energy. So another kind of energy conversion was brought forth in the scientific world. Ørsted's discovery led to a number of important inventions quite quickly because it provided a way to convert this electrical potential energy into other forms of energy. Of course, first magnetic energy, but then you also could use magnetic energy to produce kinetic energy, and I'll show you how that works. The first and most obvious of the advances was just the electromagnet. You can use a coil of wire, and by the way, the kind of wire that's used in these experiments that you'll often see in electric motors, where you see lots and lots of copper-colored wire, that's very fine wire that's coated with a kind of lacquer so that it's insulated from each other. So this is a continuous long loop of wire that you'll see in various electromotors. And if you close the circuit, you then can create a magnet just out of a loop of wire. It's an astonishing effect. You can go one step further. You can take those coils of wire and you can wrap them around so they create an electromagnet that attracts a clapper, a piece of metal. And therefore you can create a buzzer just by closing the circuit. Again, what you're doing is creating a magnetic field. It attracts a piece of magnetic metal which claps against the bell. So that was the principle, the buzzer and various other kinds of sound-making devices. The same principle, by the way, is used in the telegraph. You have electromagnets that open and close circuits. If you open and close a circuit at your end with long and short pulses, those pulses go through the wire and open and close circuits at the far end, and the same series of long and short pulses is transmitted long distances over a wire. And then we come to electric motors. Electric motors are a pervasive use of electromagnets in our society, an incredibly profound ability to convert electrical energy through magnetic energy into kinetic energy. Let me show you how a motor works. You simply have a push-pull effect of one set of magnets against another. In many simple electric motors, for example, the kind you'll find in most electric razors, you'll find permanent magnets which are fixed into the casing of the motor, And then you'll have a rotor which has little coils of wire which form electromagnets. As the current flows through these, you get a push-pull effect, and that spins the rotor because magnetic opposites attract, but the same poles repel each other. And by a very careful alternation of opposite and like poles, you can get this push-pull effect causing a rotor to work. In many other electric motors, you'll find, for example, an electric motor from a coffee grinder, you'll find that the fixed magnets are electromagnets too. They're coils of wire, so you could have coils of wire. But then there's also a rotor, and inside that rotor, there are additional coils of wire. And I encourage you, if you ever have an old appliance that stops working with motors and other sorts of devices, take it apart with your kids. See how it works. Look at those innards, because this is part of our physical world, and even though many of these devices are somewhat hidden from our view, you can understand the principles of how they work just by taking them apart and knowing these few basic ideas. An electric current passing through a coil of wire creates a magnetic field. That's the first half of the link between electricity and magnetism. Scientists expect the physical world to display a kind of order, a kind of symmetry. You see the kind of symmetry in planetary orbits when planets go around the sun, those beautiful elliptical orbits. The gravitational attraction between two masses is symmetrical. A attracts B with the same force that B attracts A. We see all the conservation laws, the conservation of energy, the conservation of mass. These are kinds of symmetry in the universe. And the same thing should apply to electricity and magnetism. Since moving electricity in a coil of wire produces magnetic effects, scientists had a strong hunch that somehow moving magnets should produce electricity. And they studied these kinds of effects very early on in the 19th century. The effect was demonstrated conclusively by the British physicist Michael Faraday in 1831 in what is now a classic experiment. I want to tell you about Michael Faraday because he's a really fascinating character in the history of science. He came to science in such a strange, roundabout way. It's really kind of inspirational. He started with very humble beginnings. He was born in 1791 in South London. He was the third of 4 children of a blacksmith. Michael Faraday's father, the blacksmith, was in poor health and could not make a very good living. The family's finances were in terrible shape. So to help make ends meet, the young Michael was apprenticed at the age of 13 to a London bookseller who taught Michael the art of bookbinding. And this was the craft that Michael thought he was going to pursue for the rest of his life. So you can imagine Faraday learning to bind books quite beautifully. You know, he was a meticulous craftsperson and so was able to do this quite well, but sitting there with all these books, all this knowledge surrounding him. And he began to read. He began to read avidly, everything he could get his hands on. He was especially fascinated by the Encyclopedia Britannica, and he began to read the encyclopedia, especially the articles on science, which he loved. Especially influential in this regard was the article on electricity in that early edition of the encyclopedia, which he was binding at the time. And you can imagine he's binding it, but he's flipping through the pages and reading it while he's supposed to be working, I suppose. It must have been quite an amusing sight. Anyway, Faraday became enamored of science. He loved science. He then began attending public lectures, notably by Humphrey Davy, that great public lecture about which I told you about a couple of lectures ago. This was at the Royal Institution of Great Britain in London. Faraday transcribed his lecture notes, the lecture notes from Davy. Lecture after lecture he would go, he'd make meticulous notes, and then copy them over in meticulous hand. He bound them quite beautifully in a tooled leather binding, and then he presented the bound lecture notes to Humphrey Davy as a calling card. Davy was impressed. Unfortunately, at that time, there was no position at the Royal Institution, and Faraday was resigned to spending the rest of his life as a tradesman binding books. But as luck would have it, in one of those freak turns of events, one of the young assistants in Davy's laboratory was fired for brawling. And Faraday was hired in 1813 as Davy's lab assistant, and that really changed the history of science. Faraday served as Humphrey Davy's lab assistant, and he flowered himself into a distinguished scientist in his own right. By the 1830s, he had made major contributions in chemistry and in physics, and he rose eventually to take his mentor's place as a researcher and as the public lecturer for the Royal Institution. So talk about emulating your scientific idol. That's what Michael Faraday did. It's said he became one of the best public lecturers of his day, following in the footsteps of Humphrey Davy. Faraday's background may have pointed him in the direction of these scientific investigations. You see, he was raised in the Sandanian religion. This is a fundamentalist Protestant sect. It emphasizes the unity of the universe. So we see this theme again. The religious background, your philosophical background, influences the kind of questions you ask as a scientist. It's been suggested that his religious background prepared Faraday to look for unity in the different physical phenomena of the natural world. So this is very much like Ørsted, who believed in the Kantian philosophy. Recall from the last lecture that it was Faraday who demonstrated that the various forms of electricity, that is animal electricity, lightning, the electricity you get from a battery, are all the same, one and the same. It's this kind of unification that Faraday loved. And again, he looked at electricity and magnetism and wanted to unify those phenomena as well. Faraday's most famous experiment took place in 1831, and he incorporated this assumed symmetry of electromagnetism. What he did is attach one coil of wire to a battery, thus creating a magnetic field. Next to this coil, he placed a second coil of wire in a circuit, but there was no battery. Even though the second coil of wire wasn't attached to any source, an electric current flowed through that second coil of wire, just being brought to the first one. Faraday concluded that the magnetic field produced by the first circuit, the electromagnet, induced a current in the second circuit. This is the phenomenon of electromagnetic induction. The exact same effect occurs when just a normal magnet is waved or wiggled in the vicinity of a coil of wire. And I can demonstrate this in a couple of ways. One is if you just take a coil of wire of this sort, even though it's not hooked up to a battery, and you start with a magnet, if you wiggle the magnet back and forth, this would actually produce a small but measurable electric current just by wiggling a magnet near it. Now that's an irregular current. It doesn't really work very well for any practical device, but it demonstrates the principle. In our everyday lives, however, we use this all the time in devices called transformers. In a transformer, you put electrical current from the wall outlet through one coil of wire. So electricity flows into this coil of wire, and that produces an electromagnetic field. You then always will see a second coil of wire nearby. And what happens is as the current flows through the one magnet, it induces a current in the second one. But in general, that current will be at a different voltage. And so this is a way in household appliances of transferring voltage of one type, for example, 115 volts from your wall circuit, to another kind of voltage. That's a transformer, a very important electrical device, something that Michael Faraday invented almost 200 years ago. The demonstration that moving magnets can produce electricity in a coil of wire immediately suggested a new procedure for generating electricity in our everyday lives. You place a coil of wire between two magnets. Then you spin that coil of wire, and electricity is going to result. This device is what we call an electric generator, a dynamo. It's the centerpiece of every electric power plant. The energy to spin those coils, to provide that rotary motion, can be provided by water. There's a hydroelectric plant where water is coming over a dam and turning like a water wheel device. That's where the spinning motion can come from. It can come from steam in a coal-burning power plant or in a nuclear power plant. It can come from gasoline, a gasoline engine that turns the coils of wire and therefore generates the electrical power. But all you have to do is rotate coils of wire against another magnet and you produce the electric charge. This was the principle behind the many home remedy electrical devices that were for sale in the late 19th century. Here's an example. What you have, the guts of this sort of device, is a large horseshoe magnet, just looping around, and then two coils of wire. When you crank a crank of a device like this, what happens is that coil of wire spins around in the vicinity of the magnet. That produces an electric current. You have to have somebody turning this while you're doing it, and then the patient would put these, perhaps to cure a headache or maybe some other part of the body, the electric current flows through the two electrodes, and that's the way of having electric current in your home, even before electricity was widespread in rural America. Electrical medical devices of this sort were sold by the tens of thousands through mail-order catalogs. The kind of power plant where you have a rotating coil of wire near other magnets produces what's called alternating current. That's because the moving coils of wire first see the north pole, and then the south pole, and then the north pole, and the south pole of the fixed magnets. And this causes electrons to slosh back and forth in the wires, for example, in the electricity that's coming out of the walls. It's AC, or alternating current. If the dynamo rotates 60 times a second, then the alternating current will be 60 cycles a second, 60 sloshes, if you will, back and forth per second. The electrons literally are moving back and forth in the wire, not continuously through it. This current is quite different from the direct current that you get from a battery. In a battery, there's always a positive terminal and a negative terminal. Electrons always flow in just one direction from negative to positive. That's direct current. In alternating current, the electrons slosh back and forth. The complex interplay between electricity and magnetism comes into play in many different ways, and the symmetry is often quite apparent if you look around you. Think about the electric generator powering a motor. In a sense, the motor, which has coils that are pushed into rotation by an electric current, is the mirror image of a generator which has rotating coils that induce the electric current. Let me do a demonstration. I have here a handheld electric generator. This is a device that has coils of wire, it has permanent magnets, and you rotate a handle, the coils of wire rotate next to the permanent magnets. And lo and behold, what happens, you create an electric current, which causes a motor to turn. The motor has coils of wire. As you pass energy through those coils of wire, the magnetic field causes them to push against permanent magnets, and that causes the motor to rotate. But look at the symmetry. If this is a generator and this is a motor, I can switch them. I can turn this, and lo and behold, this becomes the generator, and this becomes the motor. You may have noticed, if you're watching this demonstration on videotape, that I turn much faster than the motor itself turns. There seems to be a loss of energy in the process, and this is an inevitable consequence of that second law of thermodynamics. You always lose some of the energy heating up the wire slightly, friction in the components and so forth, so you never have 100% transfer of energy from one source to another. Electromagnets are used in so many ways in our lives. In every television set, in every computer monitor, electromagnets control the image on the screen. This is how it works. The image is created when a beam of electrons is flashed onto the screen, and it's rastered across. The electrons strike the fluorescent material on that screen, and the beam is then moved back and forth across the screen to convey information. The way you move that beam back and forth is with electromagnets. And if you ever look inside an old TV set CRT, you have the old monitor, but in the back side, you'll see these very wide coils of copper wire. Those are electromagnets, and that's what controls the flow of electrons. It causes the electrons to move back and forth across the screen to convey the image. Another use of electromagnets in our everyday life. Let's revisit the first law of thermodynamics for a second. Remember that energy can change from one form to another, from kinetic to potential energy, for example, or from potential energy to heat. The technological importance of the electromagnetic induction that Faraday discovered is that it provides an easy way to achieve a previously difficult conversion. Gravitational potential energy, for example, or heat, can be converted into electrical energy by this process. You have to just merely put an electrical generator in the way, and that takes the one kind of energy and converts it to a different kind of energy. Before this, people had to build their industries next to sources of energy. You had to put your power plant or your mill right next to a waterfall. You had to have a ready supply of wood and cut down forests or cart wood in to your power plant. But electrical energy can be transferred for many, many miles just over a system of wires. In the 19th century, each household had to manage its own fuel supply. Energy management became a very important part of the daily routine in 19th century life. Usually you had wood or you had coal. Rural electrification in America transformed society. For the first time, families all over America were linked physically by an energy source. And they didn't have to spend all those hours either gathering wood or other sorts of fuels, tending to fires, and so forth. The theme of this lecture is the unification of magnetism and electricity. In science, such a unification ultimately has to be accomplished by a mathematical formulation. It's not enough just to show phenomenon. You have to show equations that describe in more quantitative detail what's going on. And this lets me conclude the lecture by introducing yet another famous British physicist, James Clerk Maxwell, a Scottish physicist who transformed our way of thinking not only about electricity and magnetism, but about other phenomena as well. He set down an elegant mathematical formulation of electricity and magnetism in the 1860s. Let me tell you about Maxwell. He was born in 1831, the very year that Michael Faraday discovered electromagnetic induction. He was born in a well-to-do Edinburgh family. He was educated at the University of Edinburgh and at Cambridge, and he spent much of his academic career teaching at Cambridge. In 1871, he was appointed to be the first professor of experimental physics at Cambridge, and he also started the very famous Cavendish Laboratory, about which we'll hear a lot more in subsequent lectures. He died in 1879, the victim of abdominal cancer at the age of only 48. Maxwell's great work was the presentation of 4 equations, Maxwell's equations of electromagnetism. These equations are very complex mathematically, and they're couched in the rather abstract language of force fields and vector algebra. But we can describe these 4 equations in words, just everyday words, and I hope that they will bring to you the power of what he tried to do. The first equation is just a restatement of Coulomb's law. That is, a force exists between any 2 electrical charged objects. The force is proportional to the charges. It's inversely proportional to the square of the distance between the charges. The second equation describes the magnetic phenomenon and says that every magnet has to have 2 poles, a north pole and a south pole. There are no magnetic monopoles in nature. The third equation says that changing an electric field produces magnetic effects. And the symmetrical fourth equation says that changing magnetic fields produces electricity. One of the great wonders of mathematics, one of the things that makes mathematics so powerful in science, is that it can lead to unexpected insights. Sets of equations can be manipulated through algebra and other sorts of mathematical processes, and you can certainly learn new things about the natural world that you never suspected before. And this is what happened to James Clerk Maxwell. He manipulated his 4 equations and found that one possible mathematical solution to the way electricity and magnetism works is a wave. And because constants are built into this equation, he found that this wave had some very special properties. Indeed, the most distinctive property is that the wave had to travel at 186,000 miles per second, the speed of light. As a result, from very esoteric sort of mathematical reasoning and describing these phenomena of electricity and magnetism, Maxwell discovered the nature of light. Light is an electromagnetic property. This was an astonishing discovery about which we'll learn more in the next lecture. Let me summarize. In this lecture, we've seen that 3 great discoveries of the 19th century, discoveries linked electricity and magnetism, these seemingly unrelated phenomena. First, we had Hans Ørsted in 1820, showing that electricity flowing in coils of wire produced magnetic effects. This discovery led to the electromagnet, to buzzers, to the electric motor, and many other technologies as well. Then in 1831, Michael Faraday demonstrated how a moving magnetic field can produce electricity through electromagnetic induction. And this led to electric generators, transformers, and many other essential devices as well. And then James Clerk Maxwell systematized all these electromagnetic phenomena. He found the relationship between electromagnetism and light, and that's going to be the subject of the next lecture.